Good afternoon, everyone. Welcome to another RISPI webinar. My name is Sudha Niles, and I'm part of the senior leadership team at RISPI. I oversee the products and data systems, and I'll be a host for this webinar today. Before I proceed any further, I'd like to acknowledge the traditional custodians of the land where we meet today. And for me in Perth today, that's the Whadjuk Noongar people. I would like to pay my respects to the elders past and present, and I extend that respect to Aboriginal and Torres Strait Islander people with us today. As the rail industry continues to seek safer, smarter, and more efficient operations, artificial intelligence is emerging as a powerful enabler of real-time decision support. Across industries, AI is already being used to detect hazards in autonomous vehicles, predict maintenance needs in aircraft, and optimize network performance in logistics. And its potential in rail is now being realized. This presentation shares key insights from 4AI Systems' recent mainline trial on Australia's East Coast, where cutting-edge AI technology was deployed in revenue service to enhance driver situational awareness, and other trials that they've conducted, not only in Australia, but also around the world. With AI and deep learning software specifically designed for rail, the system translates real-time sensor data into actionable information, which is delivered directly to the driver, in this particular case, through an intuitive interface. The findings demonstrate that while AI remains a rapidly evolving field, mature applications are now available that can significantly enhance operational safety and support future rail train control strategies. This trial represents a meaningful step forward in integrating advanced digital technologies into today's rail operations. Before any further, let me introduce the presenter today. It's Mark Wood, the Chief Technology Officer for 4TEL and 4AI Systems. Mark has worked in the business since 2004 and is responsible for delivery of major projects, customer management, and managing subdivisional teams. Mark has been 4TEL's key project delivery manager for Transdev System Ferries, Tata Chemicals, Newcastle Light Rail, Transport for New South Wales Port Botany OPMS, to name a few, and was critical component to the project delivery of New South Wales Country Regional Network. He has been instrumental in driving 4TEL's research and development activities, leading to the formation of 4AI Systems. More recently, Mark has led successful trials of 4AI Systems AI technology with Pacific National, Rio Tinto, and New York Metro. Before I hand it over to Mark to do the presentation, let me remind you that to put your questions on the questions tab that's available on the presentation on Teams, and we will address them when we get back throughout the session at the end of the session. Mark, without any further ado, let me hand it over to you to start the presentation. Welcome.
Thank you, Sudha. Thank you for that introduction. And yes, today's focus is all about looking at our insights that we've found as we've been trialing AI in the rail network. And as Sudha said, there's a lot of technology that's being used in other industries, and we're starting to realise some of this now within our own rail industry. So what we're going to look at today is, before we get into the insights and all the fun parts of the demonstrations themselves, just talk quickly on why AI on trains. Why is it helpful? Why would we consider putting additional technology that requires maintenance and interfaces into the driver's cab? Why is it important to help us continue to improve both operational efficiency and safety? A quick overview of how we got there, because all of this technology, whilst it's used in other industries, it doesn't just get turned on and miraculously worked. Then we'll get into specifically how the system that we've trialed works, what then the driver is displayed within the cab, and then get into the fun parts of the trial demonstrations and what is actually seen both by the system and in the driver's cab at that point in time. On this first slide, you'll also note, and you'll recall from Sudha's introduction, that I work for 4TEL and 4AI, and there's a quick linking of how those two companies fit together Given Fortel started operations in 2000, and we formed 4AI specifically in 2021. So why 4AI, and what's the immediate business case for AI systems and rail? And we use a catchphrase for doing boring better. So one thing with an AI-based system is its focus is looking out in front, observing and perceiving the environment, and providing that information to back-end systems to allow the information to be passed based on business rules to drivers or other systems. So the key part of this is the system never gets distracted. It does the same thing over and over again. It's not distracted by onboard systems that have the potential of buzzing and beeping and distracting a driver. It is that second set of eyes to provide that important situational awareness improvement to the onboard. Also, because we're able to use various types of sensors, and you'll see this shortly when I talk about how it works, we're able to supplement better visibility and provide that information in the decision making that the system is looking for. We also are able to load a digital route map and location information on board. So this is what we call the master infrastructure data set. You'll hear me talk through that when we go through how the system works shortly. And all of this combines together to provide the ability to support real-time monitoring and onboard alerts, and also remote alerts as well. On top of that, we continually can monitor all of the infrastructure as the environment that we're perceiving and driving around at that point in time, and provide automated event reporting, again, whether it be on board to the train driver or remote to remote control or onboard system, other onboard systems. And the good thing about this technology is it's completely network agnostic, in that all we need to do is get the map of the environment that we're operating in, and then the perception is able to go from there. So how we got to where we are today and we're able to do all these great in-service trials on revenue trains, we started with a prototyping and discovery phase where we went out and captured information to see if our ideas of what we thought of localization and perception can be brought to onboard the train. And here's some initial images of both our field tests and initial prototyping on board, as everyone can see there, the heritage train where we put the first Horus prototype on board that. And that was a lot of excitement. And in fact, one of the videos that I will be demonstrating today comes from some of those initial trials. How it all works. So the system itself is comprised of various sensors, both visual and movement sensors. The top right-hand side of this slide, you can see two different sensor bars and the 5 visual sensors. So there's 2 thermal and 3 color cameras that are fused together to create an onion layer visible spectrum out in front of the train. So you see that second image on the right-hand side is highlighting how we've got those cameras that look both near view and supplement each other looking out at long range. And again, we've got examples of this shortly, which will highlight exactly how this is working. So all of that information, including our positional information from the GNSS, accelerometers and gyroscopes, get fused together to give the AI an understanding of the environment it's operating in and the visual perception of what's around us. That allows us to anticipate and check for any upcoming and registered infrastructure. And you'll see one of the examples later on in the presentation, also the looking for infrastructure that we may have or may not have in the database as well. We can use both visual and spatial means to position ourselves on the track, look for hazards that apply to the track. And again, there's videos that describe this later on. Issue any alarms, both in cab, and if we're tied to a braking system, as the bottom example shows there, where we're tied to what's called enforcer, we could apply brakes if the business rules are dictating that. And then on top of all of that information that's gathered, it gives a great tool for subsequent investigation into any issues that may have arisen during operation. So this is where that information can then tie back to the control center again, as is in the example at the bottom of the screen, pass information back to the control center and have a full picture, not just from the onboard staff, but also in the control environment. As I mentioned, Horus itself is made up of 5 visual sensors, and this is what Horus can see. So if we think about that from ourselves, our own eyes focus in different focal lengths and different distances automatically. We have overlapping sensors that allow us to look not only close, so you can see the center wide camera on the top left-hand side, then the far right-hand color image is what we call the mid-range camera that goes out to a few hundred meters. And then the color camera in the center, the RGB10, that looks out and can see vehicles beyond 2 kilometers. Then the bottom 2 cameras are both different fields of view that overlap our color cameras above, but in the long wave infrared spectrum. So that allows us to see things in inclement weather or of a night time specifically. So I've described how the system works in words, but now what we're going to do is we're going to run through an example of how the system operates in live onboard operation. So the video that's coming up here, we have a lot of colors and a lot of information on here. I'll just run through at a high level what all of this is. So anytime we see colors that are yellow, red, or green, all of that applies to our operating track. So the track that we're on, and then infrastructure or information that is relative to me as the train. Any of the purple colouring is what we call adjacent infrastructure. Now that's infrastructure not specific to where I am currently operating, but it gives me visual information and representation that can help me position myself on the right track. As we can see here, I'm on the up main and I've got the down track to the right-hand side, and that's in purple. On the top right-hand corner of this visual display are any upcoming warnings or information that the system is looking for and may perform actions on. Then the top left-hand side is our current speed, and then we can see there a list of upcoming infrastructure. And if you recall, I talked about what we call a master infrastructure data set, and that's where we queue that upcoming infrastructure. So if we can look ahead on the image, in the center of the image, I can see a number of circles. Those circles apply to the system focused and looking in that area for that specific infrastructure that we're going to make decisions on. Now that has 2 purposes. One of those purposes is so we can reserve a lot of hardware function for looking for objects we don't know about, but also looking specifically at those objects that we need to know about. If we don't detect them, we can perform other actions. Also, during this footage, during this demonstration, we had no connection to the below rail infrastructure. So as this video plays through, you'll see a lot of things run through, and I'll actually play this video twice because there's a lot of information that we need to consume over this period. But there was no information being provided from the below rail signalling systems. We'll see here that when I press play on the video and we move along at along the track, we'll see a lot of change in colour. And as I said, I'll jump back after this and we'll talk about specific elements that operate through. I'll just hit play now. Okay, so that was the video through Cowan specifically. So those of you that are familiar with the train line between Newcastle and Sydney, so Cowan is a station in that area. So as we travel along, I mentioned about the circles, and you'll see them change as we detect objects into rectangles and give us a positive colour. You'll also note that what we call virtual trip stop, that was where that green line is, that was red previously, if we didn't detect those aspects, or if we needed to, or if we saw that they were red, we could instigate information to the driver in the cab, just like one of the mechanical trip stops where it would trip the air. We could also trip the brakes if that interface was available. As you'll also note on the left-hand side, as we detect that infrastructure in that area that we're looking for, and we get the positive colour, again, green, yellow, red for the track that I'm operating on, we're just colouring that information as we travel along. One thing to note that I did neglect to mention at the start of this information is not what we provide the driver. I've got a few slides shortly that illustrate how we represent this detected information for the drivers. Okay, we'll just move along. You can see as we're going along here, we detect the coacting signal underneath it, also our adjacent infrastructure, some speed signs. Then you'll notice we're looking for a set of points. So 64 points at this stage. As we go forward, you'll see those points, once I get to there, are now positively detected. And they're detected in the normal direction or normal position. And as you can see, the track continues on. If we detected those points in the reverse direction, we would head down that adjacent track and that green center line would move around to that adjacent track. You'll also notice there is a vehicle off in the cess there. Because that's on an adjacent track, we colour that in an aqua colour because it's not of concern at this stage. If those points happen to be set in the reverse direction, we would actually, or if the business rules were set up, we may potentially change that to a warning colour. So something that then the system is more actively monitoring, but also you may provide that warning and information off to the train driver as we travel through. You also see as we go along, we detect the next set of points, so 63 points as well as we travel. The vehicle becomes closer, and as we get closer to that vehicle, you'll see there's a second one behind it, and we detect it. But again, because they are on outside where the business logic would provide those as a warning, we're detecting and monitoring them, but they're not providing any concern at this stage. So that is an overview description of how one sensor, and remember from the previous image, there are 5 sensors doing all of this information, how one sensor is displaying and detecting all of the operational information and providing that. We then send that back to a driver's display. Now, this driver's display is something specifically we have put together in conjunction with Pacific National as well for use as part of the project for the North Coast Line, but also we worked with the drivers specifically to put information that is only appropriate for what they have control over. Now, one thing to remember is in a driver's cab, the only things a driver can do is they can speed the train up or they can stop the train. Which path the train takes is all up to the network control center at this stage. So just to describe this display and how we provide all of that complex information that I showed in the video back to here. So we have what's called our master infrastructure data, which is giving us this speed curve in the middle of the screen. So the allowable speed for the train as it travels along. We also, on the right-hand side, project that next upcoming piece of infrastructure that relates to me. So if you recall that upcoming infrastructure list we're talking about, that would be the next one, which in this instance is MK21. I also have the current train speed displayed in the middle of the screen and also on the left-hand side of the graph depicted by that triangle. So it aligns directly with the braking curve. Where I've got colouring under the graph, that means we've positively detected an aspect. So beyond that signal, which that line there is MK21, that's proceed. You can also see before that signal, which is illustrating what the previous aspect's colour was. So this gives a situational awareness to the driver that if I have forgotten what the previous aspect's colour was, I can quickly look at the graph because that's how I'm deciding how to drive the train as I go ahead. And in this long section where you can't see that next signal, that helps the driver predict what they need to do up ahead. Also in the bottom left-hand corner is the track kilometre that I'm operating on, and then the projection ahead of me 4 kilometres out. Now, a lot of this is configurable, but this was based on feedback from the drivers in giving them that look ahead of 4 kilometres. However, that's when everything's operating in a perfect world. There are times where we need to provide warnings or alerts and alarms. So in this instance, this is just a warning where we're monitoring our speed in the environment we're operating in, and we're going over that speed. If it was an object or an obstacle or a red light or I was going to SPAD, that would come up in this same banner area, but instead of being yellow as a warning, it would be red. In this instance, it's an example of where I've detected my red aspect 700 meters in front of me. I'm exceeding the speed curve. That means I'll be able to stop for that red aspect. So the illustration to the driver, independent of all of that complexity that the AI is doing and looking at in front of it, is simplified into that alarm. If we're tied to the braking system, in this instance where the brakes would be applied, if it was just to tell the driver to apply the brakes, they would be just saying apply brakes, and you would get an audible alert that goes along with that. Another display is operating in and around complex yards for the drivers. And this is the only time where video is ordinarily displayed on the screen. And this is an example where we're operating out of a yard. We're detecting the specific lay of the points, and this is a short video as well. These points here are in our trailing direction, our facing set of points up here. This points display on the right-hand side was the last facing set of points in the position they were set in. I'll just press play and we'll see the video travel along. So we're still detecting those trailing points. However, our update for the position something is facing will be our facing set of points as we get near it. So you can see there the detection of the facing set of points around to in the reverse direction as we head around on the other line. And again, that was all done without the input of a signaling system. That was all done with the visual sensors, those 5 visual sensors that we had on board. If you also had the input of a control system, that could be used to confirm in the system as well. Now, for the display, this is a short video just to highlight what the driver is seeing as we're operating within the operational environment on a live track. So we can see the DMI in the middle here with the graph display and infrastructure out in front of us. I'll just hit play whilst that is going through. You'll notice the system is counting down on the right-hand side here. You can see the countdown towards the signal as we not only detect but associate that aspect, which I'll talk about shortly. You can see that the graph automatically updates to project up to the next signal. And as you can see, the display itself, integration into the existing onboard systems that are on the trains we've been trialling with, it fits within that driver's cab environment nicely. Okay, so we've gone through how the system works and how do we display key information to the drivers at the appropriate times. But before we were allowed to get into trialling in revenue service, as we would all understand in the rail world, we have to jump through a number of key components to ensure that it is safe to operate. So as we can see here, a few key things we needed to firstly demonstrate to our clients that the system was able to operate without impacting operational safety and reliability during revenue service. Remembering that the system is operating on trains that are being used to generate revenue for our clients. So these aren't just test trains, this is operating in the live environment. So as part of that, to demonstrate these things, we had to go through formal engineering approvals for both the mechanical and electrical components of the system to be installed within the rolling stock. That included, where applicable, matching the standards and getting standards approvals as well. So things like where we're installing equipment on rolling stock for EN 50155, and then wherever there was safety included, that's the safety standards that apply to that as well as the flow on EMC standards. Once we jumped through all of that, we then looked at the data security components, because one thing in this modern world with technology like this, and we need to monitor it for the continuous operation, is ensuring the appropriate data security is applied to the system so that any sensitive information is protected adequately. And then at the end of all of that, we go on and get operational approval, which you'll now see as we go through the next number of slides of that operational approval in effect. So here are some images. It's not all of the images. Here are some images of the equipment installed in the key 3 trials we'll be talking about today. So the top right-hand one is installed in the Rio Tinto Pilbara environment as we operate on their auto haul trains. Middle is the R143 rail car, that operated on the New York subways as part of the Transit Tech Labs trial. And then the bottom right-hand corner is the installation, as you can see, on the PN class loco for the North Coast in Queensland. So one thing to note is you'll see that each of them have their own brackets and mounting, and in fact the R143 railcar was a different size to the other sensor bars as well. And here's some pictures of the different customization that we've done as part of not only these trials we're going to talk about today, but other ones that are currently underway. You can see that the form factor can change slightly as we go through the different installations, and also the size to fit in with the loading gauge that was required for that installation, and even down to the colour, as we can see by the bright red one at the bottom, is able to be modified. Okay, so the first video from the trials in effect in revenue service is one that we did as part of the Rio Tinto program. This video goes through a number of scenes that are just anecdotal or data that we've captured as we were travelling along, some fixed and static tests that we did throughout the project length, and then it finishes off with a few other cases that the system was able to be used for. Now we see in this video, I'll just hit play, this one is just highlighting both the colour and the thermal camera and their use even in daylight, how beneficial they are. Then there was some static testing that was conducted in the yard. These people in the car was actually about 1 kilometre from the train. This was static testing within the yard itself over in the Pilbara. And as you can see, with the person that's walking in between the track, they were specific tests we were doing to demonstrate that rail-specific neural networks were able to consistently detect a person walking around the tracks, because we actually demonstrated the networks that were taken off generic visual identification for vehicle operation did not detect that person as they walked around the track. And as you can see there, that was proven. And then we went on to some field tests out on the running line. So this was at a level crossing on the Maitland line in the Pilbara. We can see in this scene, this is just to highlight how we tested the cow. We didn't have a real cow. We actually had to have a cow on wheels that was a movie prop, because trying to move a real cow around a live rail network would have been a challenge. So as you can see, and then we also highlight that cow, even though it was a biological mass, even in the thermal camera, the thermal was still able to pick it up. But as you see, the people in this scene as biological mass were clearly highlighted for the thermal camera. Then we went on to some specific tests from long range. So you see here we're about 1,280 metres from the level crossing. There were people and the cow that you see being pulled across. All of the componentry within inside the system, so not just visual, but I mentioned before about accelerometers and gyros, are all used to help us continue to get stable object detection and identification, even at these long distances with the general movement of the train. The train in these tests operated from 60 kilometres an hour down to stopped, and more often than not, we would have to stop about 700 metres from the test site. Okay, we'll see there we stopped. This particular scene is where we were demonstrating not only that we can detect objects, but also the positive detection of objects where you may not want to stop or act for rolling stock, in this instance like a tumbleweed. And you may ask yourself, why would we want to detect a tumbleweed? Because the train can just keep going. What we're demonstrating here is that we can positively detect the difference between a tumbleweed being in and around the track, or if in fact there was a rock that was sitting in the middle of the track. Because if there was a rock of this size, and you'll see shortly that will come out, you would want to stop a train if there was a rock of that size sitting in the middle of the track, but you wouldn't want to stop a 2-kilometre train for a tumbleweed. So that was highlighting how AI can detect the differences between those, and therefore you can set your business rule up accordingly. This again was a test. We're approximately 1 kilometre, 900 metres from this test site. Again, you'll see we're using the same props that we used for the others. However, in this instance, it looked like there was debris in the middle of the track, but in fact, there was a person sitting there. And what was a key outcome of this test is we were actually, one of the questions we were asked is, can we use this system to help drivers in this instance, because this track actually had a driver, or even without drivers? Is there a time difference between a driver seeing an object on a track and the system? This particular test, the system picked up that person, and we had our engineer on board that was monitoring this 10 seconds before the driver actually observed that person sitting up in the middle of the track. So that was a pretty good outcome and support for the system. The next one is where we are operating the train and demonstrating now not just the detection of objects, but the important part of the detection of an object around the track and how we discern using the master data set, which is what's being illustrated here, overlaid. And as we can see, we've got different business rules in and around the running line that we're on, and we can see that running line off into the future. And the reason this is important is if you are a kilometre away from a level crossing in this instance, and we can't see the track as we can't here, we're able to associate that master data and those detections with that person being both in the danger zone and then as they come out into the safe zone, as you can see there. So that's a very important association piece between infrastructure and data, even without being able to see the track itself. You'll see this one is vehicles going across that same level crossing. The next one, I'll let this one run through. We'll talk about track infrastructure monitoring a little bit later on. And then we just had some anecdotal data in some complex situations, some kangaroos, and then the last piece is just a bird that flew across in front of us. So as you can see there were a number of different situations that were detected in and around the environment. And the main focus for that was detection of objects and the association of those objects as they apply to the track. Unfortunately, for this particular trial, this is all of the information that I'm able to share at this stage. As you can see on the comments on the left-hand side, the rest of it is under NDAs. Suffice to say, you'll see similarities with the first description of how Horace operates, and we did exactly the same thing in this Tech Lab challenge where we're operating on a running line. What was nice to see here, which we don't see very often in a lot of Australian railway tracks, is some snow. So we got to test in some colder climate and snow environment, which things worked very well. Okay, the next one is our North Coast line testing with Pacific National. So one of the big challenges with these systems is not just the ability to detect an object. So we can see here on this video, just before I hit start, the detection of those aspects. So at 220 meters, which is my indication, I've got the long range camera here, so that shows it a lot closer than what it actually is. I can see the line on my driver's display. So this is what will be provided to the driver. I can also see in anticipation, I've got another aspect or signal coming up about 1.4 kilometers from where I am. Now, if you watch, when we watch this video play, you'll see the amount of movement in the camera. And one of the biggest challenges that were faced during the operation of this system and not using a signaling input, using all visual means, is associating the correct aspect to the correct track. Because one of the things that is different in the railway world compared to a vehicle is when you approach a set of traffic lights, all of those lights apply to you as you face it. Doesn't matter which lane you're in, you just react to those lights based on what's facing you. And there might be 2, 3, 4, 5 that all are showing green and indicate for you. Whereas in a railway line, those lights, you may have 2, 3, 4, 5 sets of lights at a gantry facing you that apply to multi-track territory, but only one of those sets of lights apply to you. So that's where it's really important to be able to associate the right signal to the right track. Because in this instance, if we were associating that red signal to our track, we'd be saying we need to stop. So if I just hit play, we'll see off in the distance, I can see a signal on the adjacent tracks, and I'll see the signal starting to flash on the right-hand side where the detection's occurring. Once we've positively identified that, and you'll see there now, we've positively identified that, that signal is 1.2 kilometres from where I currently am. But I've positively identified it, and I've also associated that positive identification to the track itself. So that in operation, especially while the cameras are moving around, take advantage of all of those other sensors as we are operating. And then we can see they're off into the distance. One thing just to note with the alarm that was raised there, that was actually done on purpose as part of this testing as well, in that we set the length of the train much longer than the train actually was. So the graph itself was displaying an alarm because we had to demonstrate alarms being generated, but the train driver did not do anything wrong at any point in time. And then that continues on as we approach, and we can see the level crossing as we're going there. Okay. So whilst we were doing all of these trials, we were asked a few other questions by our customers on other functions that the system could perform with existing sensors, with just adding, whether it be software modules or business rules. So this particular example here was where we highlighted a person walking in and around the corridor. And you can see here the person in front of us and the importance of having different sensors at different times. So the thermal sensor is clearly picking up that person walking around. And then the color cameras to the top and the left are finding it a little harder to see that person. However, we are superimposed on the top, and you'll see as the person comes towards us, outside of our running area is in the green, and we'll see shortly that that person walks back towards the track and becomes into a warning state because they're getting a little bit close to the line. And then you'll see as they're in our loading gauge, we become red. So that's an example of the system detecting and associating that person in association with the master data on my running track. Those alarms, events, and warnings could then be passed back on to the driver or break the train, as we have already said. One of the other big challenges we've got in Australia is we have a lot of level crossings that are high-risk environments where the trains are long and take a long time to stop, and cars approach them at higher speeds. And this is one example of where we're highlighting what a driver would see, which is the left-hand side image. And the right-hand side is the thermal. So this is all in the daytime, but it's showing the importance, even in the daytime, where we've got smoke or dust, where the additional sensors could be used to help the driver see what's in front of them, or see as that vehicle travels across. And as we approach the crossing a little closer, you can see that that starts to clear up. So we're about 400 or 500 meters away during that particular video. Now, the important thing around level crossings, and I've got another level crossing one here. This particular level crossing, you can see that around the corridor, there is a lot of trees, etc. So the driver hasn't got great view, and the vehicles also may not have great view. There are level crossing lights up here. This one is not boom gate protected. It does only have active lights. And in fact, when I hit play, when this vehicle travels across, those lights are actually flashing at that point in time. So that driver continues on. As you can see, I'll just hit pause here. Once we get that car back in sight, let me hit pause. You can see the car itself is 300 meters from us as we first detect it. So it does look closer because we've got our long range camera up, but those lights were flashing. So it is one of those things that if we were able to, if that car were to slow down and end up on the main or the active line, If we were even able to slow down to buy that car a few more seconds, as we say on the left-hand side, that few seconds may be the difference between a catastrophic incident or everyone getting to walk home at the end of the day. Okay. The next one you saw on the Rio footage, I had a short clip of this, but this is because the system has not just visual sensors, we have accelerometers and gyros, we're able to sense the motion of the train and what's normal in the operating area and what's not. So this particular video, we can see the three graphs, three different axes of the gyro, and then all of that combined together to build a picture of what would be normal and what is abnormal. And you'll see as we go past those red peaks that the camera also moves a lot more. So there was a deflection in the vertical direction of the track. So what's important here is by just having these sensors installed on board, whilst the primary objective is about visual and perception for helping the drivers and providing information back to braking systems and the control center, the other data that is captured as part of the normal operation could be fed back to maintenance environments, and where things exceed certain thresholds, that would give the maintenance environment the ability to not just have a look exactly where that peak is, but also then go and look at video to see whether it's a vertical, in this instance, which it was, pumping of the track, or if in fact it was horizontal deflection of the track as well. And that is all geo-referenced as the train operates around. And you can set specific geo-reference normalities dependent upon where you're operating, because those same deflections as you travel through a set of points would be normal. So you would have to have a different threshold in those specific areas that are geolocated. The last example of additional functionality that we're able to use our AI for was part of the program that we're doing on the North Coast, which is for what's called the ATP modernisation program. As part of that, we have to go through and validate all of the master infrastructure data that is used to make decisions within the system. So this particular video, the right-hand side is an input from the ATP system. So it's seeing much further than we can visually see in front of us. The left-hand side is our geo-reference master data overlaid on a video as we travel through. And I'm just going to skip forward to where we get up to the infrastructure itself. So we can see here, we've detected a speed sign. It's 60 kilometers an hour, so there's nothing wrong with that. We can see that the actual master data by the DMI is 60 kilometers an hour, and we've mapped that 60, so all's okay. One thing I'll note before I go further, we also had the data set up so it showed the adjacent line speed, not the main line speed. The driver did not do the wrong thing at any point on this track. This was for us, again, to test the system that is able to be used for data validation. So as we go around the corner, we'll see up here, I'll just speed up to where we get up to the next bit of next area. We can see the master infrastructure data. So if you recall back to my original description, where we're looking for infrastructure information, in this instance, the next signal is WE27, which we can see on the DMI there, is yet to be identified by the visual means. We have already got this information from the ATP system. So as we get closer, again, as I mentioned, just ignore the warning because that's programmed in to actually do that. So we'll see you shortly. We've positively identified WE27 and that's all okay. So we've verified that infrastructure. And from a distance perspective, we have all of that calculated. We can also see we have points up ahead of us and we have some speed signs. You'll note that the 25, if I just go back here, initially the 25 was hard to see. So it wasn't until we were really close that we positively identified that. However, it was there. Then the points. So we'll notice now as we travel through, and I'll speed up to the next area, again, the 70 kilometers an hour, that's incorrect for that area. So that was flagged. As we go around the corner, we'll see we're looking for WE23, but if you recall, whenever we see purple, that's not on my track. And you'll notice that my next signal is WE21 and it's 446 meters from where I am, but I can see that there is a signal just here. And we, as the AI, has detected that and said, hang on, that's close to my running line. I need to mark that as unknown so that we can have a look at that later on. That gets flagged. We then go and have a look at the data. And in fact, it was found that the infrastructure data that we were provided was missing this signal, which was WE25. So this was a demonstration of us using the AI to go through and run through an area and flag anything that looks to be wrong. So not only can it detect what it does know and what it thinks is there, it can also pick up things that it recognises and flag those for further investigation later. And we'll see as we go around the corner, WE21 up further. So what we've gone through today are all of those demonstrations and a few short clips, because there is hundreds and hundreds of hours of data that we've got running on all of the trials that we've done that have demonstrated how our location and route assurance works within the system to position ourselves on the track, then how we can detect intrusion and detection, monitor our performance or our speeds around the network. We also can provide that authority enforcement, if you recall back to the trip stop or the demonstration on the north coast where we were detecting aspects as they were coming up ahead of us and where we need to brake. We can also monitor the infrastructure, which is the example that was provided towards the end in regards to the track being incorrect as far as the vertical deflection was concerned. And then all of that is recorded on board so that we can do any future investigation or checking, as we did with checking the AI infrastructure data conformance and data validity in that last example that I provided, to allow us to then confirm that the master infrastructure data is correct. And the key part of all of this is that support for the driver to allow the AI to continually do the same task over and over again. So as I mentioned before, to do boring better. Thank you. Back to you, Sudha.
Thanks, Mark. Fantastic presentation. We got lots of questions. That's not unusual. I'm sure, Mark, you would have expected a lot of questions. Now, I'm going to start with a couple of my own because I get to facilitate this. So I'm just going to get priority over this in this scenario. But look, there are about 20 over questions. Look, I won't be able to cover all of them. So if those of you who are watching would like to sort of use the arrow key to sort of vote up those questions, then I'll quickly call them out. I guess I'm looking here, Mark, from a big picture point of view with regards to safety validation and safety assurance. And obviously, I mean, this has been, while it's a trial, it's also performing in the live network. So
Yes.
what sort of safety validation and assurance were used to assess AI systems performance during the trial?
Yes, okay. So from a software perspective, we can use the traditional standards for safety validation, so EN 50716 or the old EN 50128. And the process itself in how the software is developed falls in line with those existing standards. There is a new standard that's coming out specifically for AI operation within functional safety. I think that's 5.4. I can't remember the exact standard, but that's one that, as far as defines how you go about training and validating your networks. So the AI pipeline itself and how that works is well defined, from a sense that you have to ensure you have both independent data sets for training, validation, and testing, and then you go on and do real world testing as well. And the other benefit to our configuration specifically is ensuring that, like any functional safety system, you've got independence in sensors and then independence in processes that are around those sensors. And again, that aligns with our traditional railway standards that we talk about, 129, 128, 126, 50716. So yes, the software itself, as I said, has been written to comply where possible with that. And now with these newer AI standards coming out, we're looking to see how we comply with those. So yeah, it's a foundation of everything we do.
Which brings me, which is fantastic on the standards point of view, Mark, which brings you to the next question. Okay, one area is about the standards and the compliance with standards. The other area is this whole area of fitting into the existing regulatory framework.
Yes.
And I've noticed that this is fairly written out in it's been a trial and defined as a trial at this particular point in time.
Yeah.
How much work do you need to do from here to make it through the regulatory framework to actually make it production? Have you guys done any work in that space? You know, what is that going to look like in the future?
Yeah. Yep. So yes, there's been lots of work done with the regulator, specifically here in Australia. Also, we spoke to the independents over in the US as well. But if I focus on our Australian side of things, what's required? So like any implementation of a system, dependent upon the functional safety aspects of that, it goes through the existing safety management systems owned by the operators, with oversight from the regulatory bodies. The importance of how we've run our program so far, in every step of the way, the current regulator has been involved in demonstrations. We've had open door as far as questions have been concerned, and not just as a once-off, at each step of both demonstration and what it would look like to get to full operation. But the full operation part also encompasses the maintenance and delivery as well. It's not just about the operational safety, it's ensuring that whole life cycle for the componentry is supported. And fortunately, the existing safety management systems of the operators do provide guidance about what's required, and then what information and evidence the regulator is required to be comfortable that they're satisfying their own safety management system requirements and that the system is safe to operate. You're on mute, Sudha.
Is there current implementations that are working towards a regulatory sort of endorsement at this particular point in time? You don't need to mention that.
Yes.
Okay, there are a couple that are working towards.
Yeah,
okay.
There's ongoing discussions with the regulator for further rollout and endorsement. Yes.
Okay, I'm going to do some quick fire technical questions that are here, and I hope I'm picking the right ones. How does the braking algorithm cater for all the different types of loading requirements?
Yep. So the braking algorithm takes the input of a few things. So one is all of the braking characteristics of the rolling stock included in a train. So the locomotives and the wagons themselves. If it is ECP fitted, that has a different braking profile. And then the weight of the overarching train is taken into account as part of the calculation. So it can be on a train by train basis, or if you've got fixed consists, it will take a worst case scenario for both loaded and unloaded.
There's a lot of conversation about digitization of train control systems and ETS.
Yep.
Do you foresee any sort of integration of this type of projects into that conversation? Where do you guys foresee for this?
Absolutely. The ETCS, or any control-based system that provides authorities out to an onboard. So ETCS is just one system that does that. There's plenty of others around the world that do similar things. And in fact, the ATP work that I was talking about on the North Coast is a similar principle as far as providing authority to the train, so that the train knows where it needs to stop to operate safely. But what the AI brings on top of the signaling system and the information that the control systems provide to the onboard is that additional element of perception. So one thing those existing control systems can't provide is what's happening in the environment around where I'm operating as well. So coupling all of those regimented systems for providing authority management to the train, couple that with the eyes that never get distracted, never bored, do boring better, as I say, to help the drivers, sort of gives a full complement of what a system should look like in the future.
I mean, obviously, driver alertness is a key part of a lot of the conversation in this scenario. Is there any specific work that you do attached to vigilance systems, or how they are responding to vigilance, or any of that kind of work that you've done?
So as far as looking at the driver with cameras, no, because we see that a driver being provided information about their operating environment, and if things are outside the operating parameters, i.e. you can break the train if the driver is incapacitated, those existing vigilance systems of button press, etc., would still comply. We can integrate the system as a task-oriented, so if they're interacting with the screen, that could provide a task-oriented input into the vigilance reset. But we've found that providing the driver assistance rather than looking straight at them has been a big benefit to ensuring that it reduces any opportunity and risks associated with what could occur in SPAD. And one of the key things with the system is we talked about ETCS, which is providing onboard authority from control systems. What we're also doing here is fitting into the interim whilst we roll out those more complex systems so that we can help the drivers reduce the risks that are associated with SPAD, which is improving their situational awareness and alertness whilst they're doing the other tasks. Drivers don't go to work to do the wrong thing. They don't go to work to SPAD. So if we can provide that assistance that's not punitive but is helpful, that then ensures that the operating environment is supported in the right way for the drivers to go about and focus on their key tasks.
Thanks, Mark. I want to throw something on about degraded working. And obviously AR systems learn from the ongoing operation, but there could be multiple categories of degraded working that the system may not have encountered before. How do you deal with those sort of low frequency, high consequence sort of events, and how does the system deal with that in scenarios where the signal is not inoperable and they're operating under train authorities? How does it cope with that? How do you train that to make sure that it is capable of addressing those kind of issues here?
Yeah, absolutely. Infrequent events are a challenge to get training data, but where it's really important is the ability to train your system to be able to generalize adequately. Because like us as people, we don't have to see the same scenario time after time to make an appropriate judgment, and this system is no different. So part of the reason we have multiple cameras and multiple sensors is to be able to overcome the weakness of any one sensor in different operating conditions, and the other sensors support it, or in failure. So where we do have a camera were to fail, for instance, the other cameras do support that. Then you talk about environmental conditions like fog, heavy rain, etc. Again, which is why we have multiple sensors to overcome those environments. So the good thing is, from a vision perspective, is everything still looks the same, even in some of those inclement conditions. What changes is how far you can actually detect them, more so than whether you can or can't. So if we can get in very heavy weather conditions, we can see a lot further than the human can because of the other sensors that we have. But the challenge is it's still degraded to a level. So instead of seeing 2 kilometres down the track, you may only be able to see 500 metres. But it's still 450 metres further than we can see as a person. So we can still provide that additional support. Bearing in mind, if you've got the information from the control system, you already know where your authority limits are. So the perception system is really operating as a backup and a support to that to help those other things that the control system knows nothing about, which is every other object in car and vehicle and person and track worker and all of those other things that are around the track.
Final question. Like every other technical aid or support tool that is available, there can become an over-dependence on them. And how do you deal with that risk? I guess it's a bit of a human factors question, but how do you deal with that kind of errors or that kind of over reliance, and whether a system like that can support that or self-identify those things?
Yeah, absolutely. And this is a common question for many systems, that over reliance. Reliance in the first place is a good thing in that the system is proven and people are comfortable that it's operating correctly. So being reliant on a system isn't a bad thing. Being over-reliant upon it where it can make errors, but that's where our primary focus from a human factors perspective in this reliance is only providing information to the driver when there is something the driver needs to do with it. So for instance, if there are things that occur that have no impact on the driver's decision to accelerate, slow down, whatever it may be, is not providing information at that point in time. The other part, if you recall, by not providing video to the drivers, just providing a simplified display for information that they are required to act upon, it reduces that information that they could rely upon. Oh, well, I can see the video is seeing everything I see, so I can not worry about it. So it's disconnecting at times. But at the end of all of that, you can't overcome human nature in every way, shape, and form. And if the system is proved to be reliable, then the most important part is people can rely upon it, but still ensure that the rules and procedures in place infer that the drivers are still ultimately responsible for the safe movement of the train.
Mark, it's been an absolute pleasure talking about this. I think with all the questions that are coming through, we could talk for another half an hour or more. We don't have time. I do apologize for the questions that we have not asked. I'm sure we will try and get the copies and maybe have Mark to sort of address some of those queries and make it available. Once again, Mark, thank you for taking the time to come and present on this trial and an important piece of technology that we are using for the future. For those of us here, thank you again for participation. The next webinar is planned for the 26th and 2nd of July, same time on 2025. The title is Beyond Interoperability, What Must We Do to Realize ETCS Across the National Rail Network? And what should we do it? The presenter is Bill Palazzi. I reckon it's going to be a fantastic discussion point on where industry is moving towards interoperability. So please mark that down. Once again, thank you for participating in this webinar and hope you have a fantastic day. Thanks, everyone.
Thank you, everyone.
Cheers. Thanks.